Hi, in this video I'm going to explain what common mode rejection ratio is and actually how to measure it in this particular case of a high voltage differential probe here. But it doesn't have to be a high voltage differential probe, available on the EEVblog store by the way, discount coupon code down below. It doesn't have to be a probe like this. Any differential amplifier circuit, be an op amp or a discrete transistor one, it will have a common mode rejection ratio. So let's have a look at it. We're going to measure it with the brand spanking new Rohde & Schwarz MXO4 series scope here, 12-bit jobby, because why not? It's beautiful. So the common mode rejection ratio of a differential amplifier, in this case a differential probe, as the name suggests, is just the ratio of the differential gain of the amplifier divided by the common mode gain of the amplifier. And what is differential and what is common mode? Well, a differential amplifier measures the difference between two inputs here. There essentially is no ground reference. It is a differential signal, and a differential amplifier will have a gain of that differential signal. That's its job. If your differential amplifier has a gain of 10 and you put 1 volt differential across here, it doesn't matter where it is in the circuit, it's a differential voltage, doesn't matter about the ground reference, it'll multiply that by 10 and that's its differential gain. Now you divide that by the common mode gain. Now what is the common mode gain? Well, instead of the differential voltage across here, it is an external voltage applied to both of them at the same time. So in this particular case, okay, we've got these long leads here, and we could have like external either capacitive coupling or EMI coupling into the probe like this. So they're basically getting onto the probes in the same way. And this is why the wires are twisted like this. And if you're measuring a differential signal, it means any external noise or interference will actually, should, in theory, apply to both wires at the same time. So it's an external reference, in this particular case, reference to the grounded output of our differential probe. So the job of a differential amplifier is to amplify the difference between its positive and negative input while rejecting all of the signal, or much of the signal as it can, that is applied commonly to both of these wires. So that's why it's a common mode rejection ratio. So in theory, your differential amplifier should have an infinite common mode rejection ratio. It just measures difference here and rejects everything else. It has no gain at all of any common mode signal being picked up by both wires. But in practice, no, that's not going to happen. Just the design of the amplifier itself, and most importantly, the matching of the input resistor network in here. And I've done a teardown of a high voltage differential probe down like this. I'll link it in up here and down below if you haven't seen it. And just the matching between the resistors on here is pretty much determines the common mode rejection ratio of this probe. Because usually, like the op amps used inside here, they're usually pretty good. They're going to have like a rejection ratio of like, you know, over 100 dB or something, whereas the resistor divider drops that down to like 40 or even less. Now, a product like this HVP70 differential probe, it'll typically have a common mode rejection ratio figure measured at various spot frequencies. Maybe, if you're lucky, you might get like a response curve of common mode rejection ratio, because it's going to vary depending on the frequency. So it's going to change. So they typically, here's the values for this HVP70, and it gives us 4 spot values there. And the ratio, you can see, is, you know, like at 10 megahertz minus 40 dB. And it is usually given in a dB figure, but doesn't have to be, because it's just a ratio. So you could just use the ratio figure. And the interesting thing about this is that the common mode rejection ratio is, as I said, the differential gain divided by the common mode gain. And that actually comes out at a positive value. So why is the data sheet negative? Well, it's kind of, there's no like standard for this kind of thing. So you just sort of have to like understand that when you're talking a negative number, in this particular case, minus 60 dB common mode rejection would be better than minus 40 dB. But if you specify it as a positive one, as you might get on, say, a op amp data sheet, here's an example, you would get the higher the value is going to be better. So that positive or negative thing, just a little trap for young players, just be aware of that. Right, so how do we measure the common mode rejection ratio and verify the common mode rejection ratio of this probe? Well, what we've got is our differential input like this. First thing you want to do is, as I said, you want to twist the wires like this so that any external noise is equally picked up on both. And then you need a signal generator. In this particular case, this new Rohde & Schwarz MXO4 can go up to 100 megahertz, so very nice. So we can actually measure the 100 megahertz. This one's got a bandwidth of 100 megahertz, this MixSig jobby, which we'll measure as well. And then we want to feed the output of the SigGen into a 50 ohm terminated load so that we don't have any transmission line issues whatsoever, no reflections causing problems. I've done videos on that and how you can goof that up in noise measurements and stuff like that. So I'll link in that video up here and down below if you haven't seen it. So here I'm using an external 50 ohm 2 watt termination, a series termination, even though the scope has a built-in 50 ohm termination. But if you look down here, you could actually come a gutser because this has only like got a half watt rating. It's less than 5 volts RMS. Just, you know, you don't want to blow up your scope when you do something like this because you want to use as high a voltage as possible. In this particular case, we could do it because we're less than 5 volts RMS. But in this particular case, I'm just showing you it's better to use a high rated external terminator just so you don't blow up your really expensive beautiful shiny scope. And then we're just tapping off right across this 50 ohm terminator load here. So here's the negative terminal and here's the positive terminal. So what we want to do is connect both of these inputs together, short them together and connect to the positive input like this. Why the positive input? Because it means that we're applying a voltage relative to the output here, because the output is ground referenced like this. So we're actually referencing it to the output. So we're effectively feeding that signal generator voltage into both of these leads, i.e. a common mode signal relative to the grounded output. Because if you remember, all the grounds on your scope are all common. So this is the input signal and the output, and they're effectively joined. They're common. So what happens if I just connect one of these to here? Well, you saw it. The green signals are output. The yellow is our input there. And our green signal, it's actually going to give us an output. Here it is here. It gives us a nice, clean output like that, okay? So our differential probe is, because this one's just flapping around in the breeze, right, doing nothing, and you'll see that just jump all over the place there. And if I touch it, look at that, like we're picking up all sorts of crap, right? And you'll get exactly the same thing if you connect the negative up like that, right? The exact same thing will happen because this is a differential amplifier. It doesn't care. You're just unbalancing that input. But if you connect both of them on like that to the same point, then bingo, we've got a really small signal. So this probe isn't perfect. It's got a common mode rejection ratio. So there you go. There's a signal being amplified even though that input is completely shorted. And you'll notice that goes away if we don't connect up to that. Okay, there's our ground there, so we've just got like the inherent noise of that amplifier. And it doesn't matter what I do to the probes here, but this one, if we hook it back up, you'll notice that if I start playing with those probes, right, things start happening, okay? Like, you know, it starts like being influenced because like we've got these long leads here. That's why a differential probe with like really shorter leads is better, but these have them, most probes have them built in though, unfortunately. So what happens if I untwist those leads like this? And so we're going to get the same signal, but we potentially have more variation. Check it out. You actually get huge differences. Like if I take my hand away from that, right, you can get large differences like that. So if you don't twist the leads and keep that common mode signal, right, you can completely screw up and come a gutser on your measurement. Whether it's a probe or whether or not it's a differential amplifier, op-amp, or discrete transistor circuit, whatever it is you're measuring. Yeah, the signal conditions you're measuring here, because we're talking about very low-level signals, it's really important. Now that I've explained what we're doing and I've shown you the setup here, there's no reason to look at this anymore. So I'm going to actually go over to a remote desktop view and we'll do a direct screen capture of this. It'll just be nicer, and because I can. Ah, isn't this schmick? Look at this. Ethernet remote control. It's got a built-in web browser, so we can just go to the IP address and bam, we're in. So we can do some like configuration and file manager stuff, but let's just go to full screen here, and we can either get the with the front panel or just the screen like this, but we'll include the front panel so my ugly mug's not covering too much. So channel 1, the yellow one, that's our SIG gen there. We've got 1 volt per division, 50 megahertz bandwidth, because you do want a bandwidth limit, and this scope actually has some cool software bandwidth limiting options in it, which we might see later. And 1 megohm input, DC coupled, DC or AC, doesn't matter. And channel 2, also the same 50 megahertz bandwidth here, 500 microvolts, but yeah, no, let's just leave it on 2 millivolts there, shall we? Now you can see we've got a real fuzzy wuzzy waveform here. Now, of course, this is a 12-bit scope. You don't necessarily need a 12-bit scope for, you know, this particular application that we're doing right here, but 10 or 12 bits, more better, but we can actually go more than this. So you can actually see up here, up the top, it's telling us just that's the basic 12-bit, but we can go higher, because if I get my ugly mug out of here, we can see that we've got a HD mode down here, a high definition mode, and we can actually set that on. Whoop, oh, there we go. We instantly set it on, and you'll notice that our 12 bits went to 16 bits up here. And notice, and watch this. This is really cool, right? You notice how history mode up here. See that number history? It's taken 500,000 history samples, not histogram, but history samples. That's what the history button down in the bottom corner here is. Now, if we turn this off, it'll reset that, and look at how quickly it captures. Boom! Look at that, right? a million waveform captures just in a couple of seconds there. This scope's actually capable of 4 million waveform capture per second, and you might see this in an upcoming review video. Leave it, thumbs up down below, comment. Yeah, I've already done an unboxing video. I haven't edited it yet. There were delays, and then if we turn that off, it'll go back to 12 bits, boom, 500,000 like that. So yeah, it's really quick, really schmick. So let's turn HD mode on there. But before we go ahead with that, I'll just mention the signal gen here. Now, you want this to be as higher amplitude as possible, because the output signal that you're actually trying to measure, that common mode signal, is really low. So the higher the input signal, the better. So I've gone up to the maximum amplitude here of 5 volts peak to peak here, and we've got a frequency of 10 megahertz, because that's just the you know, a typical figure we've got in the data sheet, which we want to try and verify. So we want to clean this up a bit more, so let's do some averaging. So we'll go up to the acquisition up here, and we're actually in sample mode, so we'll go down here to average mode, and then boom, we can do like 40 averages, something like that. We can take the time base out a bit like that. You notice how it gets a little bit like chunkier when it goes. I guess that's a feature. So we've got a decent number of signals. You can see that our average there, we've got 40 averages there, and that's just cleaned that up a tad. But you can see how we are dealing with the wobblies down here, because as I said, the test setup is everything. So if you can shield it and keep the leads short and make sure that they're twisted and everything else, it's going to be better. But let's see if we can use this to get our figure. So what we need now is to compare the input signal to the output signal. That'll give us our common mode rejection ratio. In this particular case, you saw on the data sheet that it's actually negative here. So at 10 megahertz, it's minus 40 dB here. So we want to flip that around here to give the output divided by the input. Now, to measure this ratio between input and output, we can either measure the peak-to-peak value or the RMS value. Doesn't matter. RMS is, you know, it's better, it's more accurate. But you might think that we use this RMS value here, and that 1.4 millivolts like that. But I've done a video on this where that RMS value, that includes any DC offset component. So that's not quite what you want. So let's go into the measurement menu here. Unfortunately, they don't have it in the basic category. You've got to go down to the vertical there. There you go, standard deviation, AC RMS. I've done an entire video on that. So we want channel 1. We should be able to drag that to like a trash bin or something. I should be able to right click on that and actually delete. You know, the user interface, come on. But I can actually go in here like this. I can double click on that and I can choose specific type, AC RMS, like that. I do like how every menu here, you can actually set the transparency with the slider bar there. That's kind of like really groovy. And you see how in this menu here, it does actually have a trash can down here, but it's like, and then you've got to select which one you want to trash can. Why can't, like, no, you know, well, you either like that or you hate it. So let's actually get a few waveforms on screen here so it's a bit more accurate. And once again, we can turn the statistics on there. Come on, can't double click to get into the menu. By the way, one little thing I wish they had is that, where is the signal generators on? Why is that not on the screen somewhere? It should be somewhere. Look at all the dead space down here. I shouldn't have to go into the SIGGEN here to actually see that that's 10 megahertz there. It should be on the screen somewhere. Please, Roden Schwartz, add that. See, they've got all the other channels here that when they're not on, they're over here, right? But the SIGGEN's on. So the SIGGEN should actually pop up over here as one of the boxes to tell you that the SIGGEN is A, on, and B, what the settings are. It's just inconsistency there. Oops, I had the wrong bandwidth there. So we have to use the 50 megahertz bandwidth here because we're measuring 10 meg. 20 meg is a bit close to the frequency. You want to be a bit more than double above like that. So, you know, 50 is not a bad value. So we get our confuser out here and we look at the RMS value here. Don't be confused by, remember how I mentioned standard deviation before? You got to watch my standard deviation video. The standard deviation here is not referring to the AC RMS. It's referring to the standard deviation of the standard deviation AC RMS signal. So it's like, it is very confusing. So yeah, don't come a gutser there. Anyway, so we need to get our confuser out, and 883 microvolts, so or 882 microvolts, we won't get any more precision than that, divided by our input because we want a negative number, so 1.75 volts. Then we want to take the log of that and then multiply that by 20, not 10, because this is a voltage. So we get minus 66, basically. That doesn't sound right, because our spec over here says minus 40 at 10 megahertz. Why is it way better? Way betterer. Because this CMRR is what's called input referred. It's referring to the input of the actual amplifier, in this case inside the probe here, before it gets gained up by the amplifier. Now, if you noticed in the video before, we're in the 10-to-1 division ratio setting. So there's a gain of 10 in there. So we have to account for that gain of 10 in here in our dB figure. Now, you know, a good data sheet, they should actually specify that and tell you exactly what it is. Now, this is a good marketing trick, because marketing can make the common mode rejection figure sound a lot better just by saying, oh, that's input referred instead of like output referred, or, you know, so just don't get caught by that. Okay, so in this particular case, our times 10 probe over there, times 10 of course in dBs is 20 dB, and times 100 would be 40 dB, times 1,000 would be 60 dB. It goes up 20 dB for each order of magnitude step like that. I've done a video on dBs, and that's just the cool nature of dBs. So we have to actually add on 20 dB to that. So 66 minus 66 dB becomes minus 46 dB. So yes, it does actually meet that specification. So it beats it by 6 dB, actually. Not too shabby. But this is only a typical figure, so, you know, yeah, but we're actually doing better than that. So let's repeat this at 1 megahertz. So it should get better by about 10 dB. So we've got this 46 here. Maybe we'll get 56, will we? Let's see. So we want to go to 1 megahertz on our SIGGEN there. And we do want to change lower the bandwidth of our input here. So we'll go in there and we'll just drop that down to say 20 meg there. So, you know, reasonable margin, but you don't want to be too high. And then we've got to change the time base. Otherwise, we won't get enough waveforms on there to give us a reasonable value. So there you go, 423 microvolts divided by 1.8 volts there. And log times 20 equals minus 72. Yep, there you go. So you subtract, or add 20 dB to that, so it's minus 52. So there you go, this typical spec is minus 50, we're getting minus 52. Yeah, comes out. And let's try 20 kilohertz, shall we? Our figures come out at minus 52 dB. It's basically the same as what it was at 1 megahertz. So our situation has not improved. So why is it a good 8 dB outside a spec there at 20 kilohertz? Dunno. I can't think a reason why. So what I'm going to do here is I'm going to go into acquisition and I'm going to change the acquisition bandwidth. Now here's a cool feature of this Rohde & Schwarz scope. We can actually define a software bandwidth, and we'll see later how cool this is. Let's set, say, 100 kilohertz, like that. Boom, look at that. So we can now software clean that up really schmick, really nice. So we can set any arbitrary software bandwidth limit on there. So you've got the hardware over here. You can see it's put it down here as 100 kilohertz. Okay, it's overridden the bandwidth of the hardware bandwidth of the front end, which is 20 megahertz. Now it's overridden that, and it's put it down the bottom corner here, and it's put it as on the channel as 100 kilohertz. So yeah, hardware bandwidth 20 megahertz, effective bandwidth 100 kilohertz there, because we've put in a software filter like that. So let's clean that up very schmick, and it is slightly dropping there, but you know, like 405 microvolts divided by 1.79 log times 20, we're still and you add on the 20 dB minus 52.9. So yeah, doesn't meet the spec. But if we try and measure it down at 50 hertz here, which is supposed to be minus 80 dB, so it's 20 dB increase over 20 kilohertz, you can see that, yeah, it's gone to nothing. Again here, 500 microvolts per division, and there's nothing there. I mean, we can take that figure and punch it into the calculator, but like, it's just nothing there. We're basically measuring the RMS value of the noise at this point. Anyway, you can see the process there. That's how we can measure the spot frequency. Now, how can we get a plot over frequency? I'm glad you asked. We can do this using, if we go into apps here, ta-da! One of the things it's got is FRA, or Frequency Response Analyzer. So let's open this bad boy up, and whoa, yeah, we can get a plot of this over frequency, when we can also get phase as well. So we're going to put our stop frequency in here of 10 megahertz, and start frequency. Yeah, we can actually start down at that 50 hertz figure. Yeah, we can't actually measure that. So points per decade, I don't know, let's just have 2 points. This is not like total, because you could have total in there. Just 2 points per decade like that. Oh, value out of range. Why? Looks like the minimum we can have is actually 10 points per decade. That's kind of, well, it's a lot. So we set up our input as channel 1, our output is channel 2, 50 hertz to 10 megahertz. Amplitude, as once again, you want the maximum amplitude, and we're good to go. So we should be able to now hit run on this. Now watch down in the bottom corner down here, as it's adjusted, it's set to AC, and then it's adjusting the range all in real time. It's adjusting that. And you can see it's slowly plotting here. It's only a small, it's got a table and a thing. We could zoom that later if we really wanted to. But 50 hertz, 100 hertz, right? It's down in the noise. Anyway, here it comes, 10 kilohertz. So it's starting to get out of the noise there. And we can adjust the range in a minute to actually see that. And boom, we are done. So can we actually make that whoop down like that? So we can make that a bit bigger. Now, I don't think there's anything in here that allows us to set the offset there. Maybe in advanced, maximum phase, measurement delay off, real resolution bandwidth, no, delay time, no. So we can't like add in, maybe we can do some maths on that, but I'm not seeing it. Anyway, just remember that we have to add 20 dB onto these figures here. So you can see that, you know, around about 5 megahertz there, it does really, you know, it starts to sort of like, you know, common mode rejection ratio gets worse. The higher that is, the worse it is. And you can see that the red plot here is the gain. We're not too, that doesn't matter for our common mode rejection ratio, but if we actually extend the bandwidth on that, we should be able to actually see a phase reversal. Anyway, we've got our table here, so let's actually go to our 10 megahertz. So at 10 megahertz here, you can see minus 64, which is minus 44.95. So yeah, that is better. I can't remember what we got before. Is that more better? The 1 megahertz, so minus 71 is minus 51 dB there. So yeah, that meets the spec of minus 50 as we saw before. And at 20 kilohertz, 22 near enough, it's minus 71, so minus 51. Once again, yeah, we just don't have the ability to measure that low, really. So it's kind of like maybe the limitations of the hardware, measurement hardware that we've actually got here. We're just not getting that. So if we go up to the full bandwidth here, 70 megahertz of this probe, let's rerun that again and see what we get. I'm not going to go low frequency this time, so I'll start that at 100 kilohertz, shall we? So it's auto-ranging each time it actually takes these samples, which is really quite nice. So it's maximizing its dynamic range there, and it's also adjusting its bandwidth as well. You'll see that the, it just jumped from 1 to 2 megahertz, 3 megahertz, see? So it's actually software adjusting that bandwidth. This is really cool. This is a very good frequency response analyzer. So we're looking for the phase response to actually reverse here. Oh, yep, there it is. There it is. Hey, that's totally expected. Totally expected. That's a normal amplifier behavior, not just a differential amplifier. It's a normal amplifier behavior. So expected that. But once again, phase doesn't mean anything here. But you can see that, yeah, up at right up to 70 megahertz, it's minus 41, which is minus 21 dB. So it's a fairly sharp rise after, you know, once you get above that 10 megahertz, that's why they don't give you a figure up at 50 meg or 70 meg. They once again, marketing just you know, stop at 10 megahertz. I know it's my probe, but I didn't make this data sheet. It was done by the manufacturer Sapphire, who's a Taiwanese manufacturer of probes. They're excellent, by the way. They make some of the, you know, Rodin, LaCroix rebadge them, and a whole bunch of other companies rebadge Sapphire probes. They're really good. Unfortunately, this video has been long enough, so I'm going to leave this Mixig probe. I'll leave that to a second channel video, and I'll show the results from this one. So that's how you measure common mode noise. I hope you found that interesting and informative, and it's not often done. You just take it for granted from the data sheet, but if you want to verify this, you're designing your own amplifiers. Doesn't have to be differential probe. It can just be any differential amplifier, or even like a regular, you know, op-amp regular amplifier. You might have the common mode rejection ratio. By the way, it's you know how I mentioned the resistor dividers are the main contributor to that. If you're trying to actually build up a circuit to measure the common mode rejection ratio of your op-amp, for example, you've just designed a new op-amp, you know, you work at analog devices or whatnot, and you want to measure the common mode rejection ratio, well, it's going to dominate via the resistors there, but you can actually do a technique. Maybe I'll do a second, leave it in the comments if you want to see a video showing where you can actually eliminate the resistors in the circuit from the measurement, and you can just get the pure common mode rejection ratio of the amplifier. You can do this using a difference, a step difference in the power rail voltage. So that's also how you can do it as well. So it's just an interesting tidbit. But there you go, common mode rejection ratio. If you enjoyed it, give it a big thumbs up. As always, discuss it down below, and subscribe to EEVblog 2 and my Odyssey channel, where there's exclusive videos over there. If you want to see a couple of, I think I've got 2 exclusive videos of the Rodin Schwarz oscilloscope, why it's actually been delayed, because we had to actually swap it. So anyway, exclusive videos over on my Odyssey channel, if you want to have a look at what happened there. But yeah, this is really sweet scope. So yeah, leave it in the comments. Do you want to see a teardown, or do you want to see a feature review? It's got so many features, but I can show you some of the really cool stuff in this. It's going to be good. So anyway, catch you next time.